Hello everyone, welcome back to Solid State series, and this is Solid State part 24. And in this video I'm going to discuss the model questions on HCP, hexagonal close packed structures. So but before going to the questions, let us try to recollect the information which is needed to solve the questions. But here very clear, I'm not going to discuss the derivations here because the derivation part already I explained in the previous videos. But the summary, important points, the key points are problem solving techniques. What is the important information you have to remember while solving the problems? That idea I'll give for 5 minutes. After that, we'll discuss some important model questions on HCP unit cells. So here, in case of these HCP unit cells, the information what you need to remember while solving the problems on HCP. So here, if you can recollect one simple formula, most of the questions can be solved easily. What is that formula? What is that formula? That is the height of the hexagon. So we are talking about a three-dimensional hexagonal unit cells. If you can recollect the height of that hexagon, we can solve most of the questions very easily. So the height of the hexagon, so that is 2 root 2 a by root 3, where a is equal to 2r. In place of a, you can substitute this and you will be getting height of the hexagon in terms of a radius. But if you can recollect the one unit cell of HCP, if you take one unit cell of HCP, if you take, it has particles in 3 layers, and we are talking about the distance between the first layer and the third layer, that is called the height of the hexagon. So here, this is the unit cell structure. So this height we are talking about. If you can recollect, if you can remember this height of the hexagon, problems can be solved very easily. And you already know the base area. The area, if you take, it has 6 equilateral triangles. So here base area is 6 into area of the triangle, that is base area. And if it is multiplied, base area is multiplied by the height, you will be getting volume of unit cell. But whatever, you need to remember one simple point, that is height of the hexagon. This is the height of the hexagon. And you can spontaneously find a volume of that unit cell. So volume of that unit cell, this is base area. There are 6 equilateral triangles, and base area into height. You'll be getting the volume. So this is the volume of hexagonal HCP unit cell, volume of HCP unit cell. But here, if you can recollect, in case of cubic unit cell, that was only a cube, but here 6 by root 2 times of a cube. Volume of HCP unit cell is 6 by root 2 times of a cube. Otherwise, if you substitute r to r in place of a, you'll be getting this expression. But these things can be done spontaneously. And the most importantly, Z effective, if you take, Z effective is 6, but clearly we discussed Z effective is 6. So 12 corners, and each corner contribution is 1 by 6. 2 face center contribution is 1 by 2. At the center of the HCP unit cell, there are 3 particles. Altogether, there will be what we call effectively 6 atoms. And how to get the packing fraction? That will be 6 into volume of each atom, 6 into 4 by 3 pi r cube by volume of unit cell. 6 into 4 by 3 pi r cube by this, if you simplify, you'll be getting 0.74. And the packing fraction of HCP unit cell and CCP unit cell, same. And one HCP unit cell, you can see here there are 6 atoms, so there will be 12 tetrahedral voids. But the location of tetrahedral voids in one of the previous videos clearly I explained. If you have any doubt and more clarity if it is needed, you can watch that video again. And how these 12 tetrahedral voids distributed, if you see, 8 tetrahedral voids are completely inside and 4 tetrahedral voids are lying on edges. All right. And octahedral voids are also present. How many octahedral voids? 6. I told you already, this is the recollection of the formula what we discussed in the previous video before solving the problems. 12 tetrahedral voids and 6 octahedral voids. And I always suggest to remember this. For example, this is the first layer, this is the second layer, and this is the third layer of HCP unit cell. And divide this HCP unit cell into 8 parts. Divide this HCP unit cell into 8 parts. So what happened? This is H by 8, 2H by 8, 3H by 8, 4H by 8, 5H by 8, 6H by 8, 7H by 8, 8H by 8. And you will be getting some tetrahedral voids here, that is at H by 8 height from the base of the hexagon. 2H by 8, that is H by 4 octahedral void. 3H by 8 again tetrahedral voids. And this is layer B. Here we have particles of the middle layer, again tetrahedral voids at a height of 5H by 8. Octahedral voids 6H by 8, that is 3H by 4, and again tetrahedral voids 7H by 8. So my point is, you divide it into 8 parts and write of course first this is bottom layer, tetrahedral voids, octahedral voids, again tetrahedral voids, middle layer, tetrahedral voids, octahedral voids, again tetrahedral voids, and the top layer. And you can answer the questions. And of course it is AB type of packing, because the third layer is the repetition of the first one, and the coordination number is 12. And in fact this is octahedral void. You can see octahedral voids are completely lying inside between first layer and second layer, 3 octahedral voids. Similarly, between second layer and third layer also there are 3 plus 3, 6 octahedral voids. And if you see, this is tetrahedral void, this is tetrahedral void, this is also tetrahedral void, and this is tetrahedral void. Now you can see between the first layer and the second layer there are 4 tetrahedral voids, but they are not present at the same height. That's why tetrahedral voids are located at 2 different places between first layer and second layer. And you can see these are also tetrahedral voids, but they are not at the corners. They are sandwiched between the first layer and second layer, and obviously that position is called edge. And here this is unit cell. And the coordination number, if you want the coordination number, this is the particle. This is directly in contact with the 6 other particles of the same layer, 3 particles of the next layer, 3 particles of the previous layer. Hence its coordination number is 12. And here these are the particles of first layer. 2 types of voids are generated. So here blue and yellow. Blue is a triangular void, yellow is also triangular void. One type of triangular voids are covered by the particles of second layer. Because of this, you can see here yellow void is missing here. And in fact, after placing the particles of second layer, you are going to get 2 types of voids. In fact, this is octahedral void, and this red color is called a tetrahedral void. When the particles of third layer, what is the arrangement? We are talking about HCP unit cell. So the particles of third layer will be sitting above tetrahedral voids. Above tetrahedral voids. If you place the particles above octahedral voids, you will be getting CCP. But our discussion is HCP, right? And here this is height of the hexagon. Some tetrahedral voids are present here. Actually, some tetrahedral voids are present here. So this is the brief discussion. And the formula, height of the hexagon is only required. Remaining things can be calculated very easily. And the only thing is understanding the question is important. And still, if you have any doubt in the derivation part and anything, you just go back and watch the video. One video was made particularly on a HCP unit cell. Right. Now let us actually, this discussion is numericals. All important models, all possibilities I'll be discussing here. So here let us take a molecule A to B. It's a molecule, triatomic molecule A to B, and the molecular mass is given 259.8. And it crystallizes in a hexagonal lattice. The lattice constants A is 5 angstroms and B is 8 angstroms. Hexagonal lattice, he's saying A is 5 angstroms and B is 8 angstroms. The density of the crystal is 5 gram per cc density, and find the number of molecules present in given unit cell. He gave the diagram. If this is not mentioned, if the diagram is not given, straight away you can say Z effective is 6, but he gave this diagram. That means actually this is the unit cell. This is actually bigger unit cell. And it has to be divided into 3 parts. It is actually divided into 3 parts, and you will be getting a rhombus kind of thing. Here, this is divided into 3 parts. You can see here, this part is given. This part is given like this. Like this. So here, this part is given like this. And similarly here we have one more part, and this is one more part. So this is actually bigger unit cell. Bigger unit cell, smaller unit cell are meaningless, but actually this is the actual unit cell. This is the actual unit cell. You can see in that diagram also he gave only one third part. But straight away 6 into 1 by 3, 2 we can say, but we have to prove that. We have to prove that. So density is given. Yeah, density, molecular mass is given, density is given, A and B are also given, and we need to find a number of Z effective we have to find. And what is the required formula? Density of the unit cell is equal to Z effective into molecular weight by Avogadro number into volume. But the volume of this you have to find. So this is height, and here this is A, this is also A, this is A, this is also A, and base area you have to find. Here he mentioned angle 120, and there are two equilateral triangles again. Base area into height, base area into height, you will get the volume. So volume of this unit cell is equal to A square B sine 60. In the question he gave sine 60 also, right? And the volume of the unit cell. So A is given that is 5 angstroms, B is height of the unit cell, but I'm taking centimeters. So 5 into 10 power minus 8 whole power 2. B value is given, sine 60 is also given, and the volume of unit cell I got it as 173.2 into 10 power minus 24 centimeter cubic centimeter. And there are so many ways to solve, but simply we can solve like this. Density is given in the question. Density is equal to Z effective into molar mass by Avogadro number into volume of unit cell, this one. So density is given in the question, molar mass is given in the question, Avogadro number we know, volume I calculated, Z effective you have to find. So everything is provided. You can see here density is given, molecular mass is given, A and B are given, volume is calculated, and Z effective we can find. And if you simplify after substitution, you will be getting effectively there are two molecules according to the given data, right? What is the required thing? Simple logic. Density of unit cell is equal to Z effective into molar mass by Avogadro number into volume of unit cell. But here a different unit cell is given, different structure was given. So if the bigger unit cell is given, straight away we can substitute the actual volume. But he gave only one third part. So I have calculated the volume and I used the density formula. Finally, I end up this with two. Effectively, there are two molecules, right? And now let us move on to the next one. Graphite has HCP arrangement. Graphite is an allotrope of carbon. And the distance between parallel planes is 3.35 angstroms. Find the density. Graphite is a HCP unit cell. And here, what is the given data? So this is the first layer, this is the second layer, this is the third layer. And he gave this value. What is the value? 3.35 angstroms. But we know this value, H, but he gave H by 2. So H, height of the hexagonal unit cell is 4R, root 2 by root 3. But he gave not H value, H by 2. Distance between two parallel planes. So H by 2, obviously that will be the half of this, and that value is equal to 3.35. From that you calculate radius. You'll be getting radius is like this. And what is our requirement? Density, very clear. But density is equal to Z effective into molar mass of the constant particle by Avogadro number into volume. But radius I calculated, now volume of unit cell. Volume of HCP unit cell, 24 root 2 R cube, R value we have calculated, and the volume of unit cell. So this is volume of unit cell. If you simplify, you'll be getting 2.93 into 10 power minus 22. See, if one point you are preparing for a national level examination, and I'm not here to explain the simplification part. What is the given data? In the previous video also I told you. So what is the given data and how to link the data? That part only we have to do. If we cannot waste our time on simplification part. So simplification part, so here should not be done here. And I'm taking volume of unit cell, and density is equal to which unit cell it is? HCP. Z effective is 6. What is the element? Carbon. Molar mass of carbon is 12. Volume of unit cell we have just calculated, and Avogadro number. And if you simplify, you will be getting density of that graphite is 0.41 gram per cc. That means in every ml, in every centimeter cube, in every cubic centimeter of graphite, 0.41 grams of carbon is present. Once again, he gave h, I calculated h by 2. From that radius I calculated, from that volume I calculated, from that density. You just see how I'm connecting the concepts. That has to be focused here, right? And now let us move on to the next question. Hexagonal close packed atomic solid has some defect, okay, some deviation, and it's one corner and one face center left unoccupied. That means actually systematic units, if you see the systematic structure of that, there must be 12 corners and 2 face centers and 3 body center, not 3 body centers, 3 particles at center of the unit cell. But due to some defect, one corner particle is missing, one face center particle is missing. Now he's asking what is the packing fraction. Don't you know packing fraction? Packing fraction is equal to volume of atoms by volume of unit cell. Actually, how many corners you are expecting? 12. How many are missing? 1. So number of corner atoms remaining 11. Face centers, actually there are 2, but 1 is missing. So there is only 1 face center. But he didn't tell anything about body centered. I mean, the 3 particles which are present at body center, so they are not affected. Now, what is the effective number of atoms? 11 corners, and each corner contribution is 1 by 6. 1 face center contribution is 1 by 2. At the center of the unit cell, there are 3. And if you add, you will be getting 16 by 3. Effectively, one unit cell has 16 by 3 atoms. 16 by 3 atoms. I'm not talking about the full solid. It's only one unit cell I'm talking about, right? And 16 by 3. And what is packing fraction? Volume of atoms by volume of unit cell. How many atoms are present? 16 by 3. What is the volume of each atom? 4 by 3 pi r cube. Volume of unit cell, 24 HCP unit cell, 24 root 2 r cube. So r cube cancelled, and if you simplify, you'll be getting 0.658. If everything is proper, without any vacancy, if everything is proper, what is the packing fraction of HCP unit cell? 0.74. Because of missing of one atom from corner and one atom from face center, the packing fraction is reduced to 0.658. 0.658, right? Let us move on to the next question. And here, helium, actually it is noble gas at room temperature, but we are talking about the solid helium, right? So helium crystallizes in HCP with the height of the hexagon equal to 600 picometers. In graphite question, he gave h by 2. In this question, directly he gave h. Find the density. Only same model, actually. Same model for the sake of practice. So, height of the hexagon, 4r root 2 by root 3. From this radius, from this volume of unit cell, what is R requirement? Density. What is the density formula? Density is equal to Z effective into molar mass of the constant particle, Avogadro number, volume of unit cell. I already told you I will be guiding only how to link the concept, how to understand the question, what is the required formula, what are the conversions, any deviation or any key point, those things only I'll be discussing. I'm not teaching you simplification part here, right? So here the density will be 0.189 gram per cc. Here 4, because the given is helium. Atomic mass of helium is 4. Same model as a graphite question. And let us move on to the next question. And it's a previous mains question actually. 2000, I guess 2019. 2019 mains question. A compound of a formula A2B3. It has a HCP lattice. Which atom forms HCP lattice and what fraction of tetrahedral voids is occupied by other atoms? See, very clearly he's saying one is a guest, another one is host. Host means the HCP unit cell belongs to host. HCP unit cell is made up of host. HCP unit cell was constructed by host, and the guest is just occupying some voids formed by the host. It may be tetrahedral or octahedral, but he gave tetrahedral, he's saying. And now this is the formula, and according to this formula, he's asking HCP is made up of which atom? That means which is actually forming this HCP lattice and which is occupying the void. My suggestion always verify the option. Instead of deriving, it would be better you go for verification. It is only fast. So our requirement is A2B3 we should get. And what is the first option? HCP lattice is formed by A. 2/3 of tetrahedral voids are occupied by B. Now let us find the formula for this. A is HCP lattice, it is forming, Z effective is 6. And in the first option, he is saying 1/3 of tetrahedral voids. Tetrahedral, sorry, 2/3, sorry, not 1/3, 2/3. So how many tetrahedral voids are present? 12. But at this point of time, don't think how to table tetrahedral voids. Without having the clarity on the concept, there will be no use of watching this video. So 12 tetrahedral voids and 2/3 of tetrahedral voids. 2/3 of 12, there will be 8 atoms. 6 atoms of A, 8 atoms of B, A6B8, simplest formula is A3B4, but he's saying A2B3. He's saying A2B3, but for the first option, we are getting A3B4, so this is not the answer. Now let us check HCP lattice is formed by A, 1/3 of tetrahedral voids. HCP lattice is formed by A, okay, Z effective is 6. Now he's saying 1/3 of tetrahedral voids. 12 tetrahedral voids, 1/3, that is 4. A6B4, we are getting A3B2, but actually we need A2B3. We actually need A2B3, so B is also wrong. B is also wrong. You can see here A2B3 we need. And now HCP is formed by B, lattice is formed by B, 1/3 of tetrahedral voids are occupied by A. Lattice is formed by B. Lattice is formed by B. 1/3 of tetrahedral voids are occupied by A. Now B atoms 6, A atoms 4. Simplest ratio A to B3. What is our requirement? A to B3. So answer is C. C is the correct answer. And it is the previous mains question. So answer is C, and it's a single answer. Need not to try the fourth one also, but for the practice sake, I wrote there. And the next one, if the height of HCP unit cell of identical particles is H, then find the height of octahedral voids from the base of the unit cell. I gave the hint, but this derivation is very lengthy, but I gave the hint. And now he's talking about which voids? Octahedral voids. So here, this is octahedral void, H by 4. This is octahedral void, 6H by 8. So that is 3H by 4. So straight away the answer is H by 4 and 3H by 4. And the next one. An element exists in two allotropic forms. One is CCP and other one is HCP. Same element, allotropes. Physical properties are different. One is having CCP structure, another one is having HCP. If the atomic radius of element is the same in both forms, there is no change in the atomic radius of the element during formation of a CCP crystal and HCP crystal. During crystallization, atomic radius is not getting affected and it is same. Then both allotropic forms have the same. And he has given 4 options, and which property is same for both allotropic forms he is asking. And same element, same atomic radius. First, let us find the density. Don't you know how to find the density? Let us find, no issue. First, CCP, FCC, phase diagonal. Particles are in contact along phase diagonal. Root 2a is equal to 4r, and a is equal to 4r by root 2. A cube is equal to 4r by root 2 whole cube. So density is equal to, what is Z effective of CCP? 4, molar mass m, Avogadro number, and volume is A cube is equal to 4r by root 2 whole cube. 4r by root 2 whole cube means this much. And if you simplify density of CCP, you will be getting like this. And of course, what I have done is molar mass, Avogadro number, and R cube are same, are constant. That's why I separated. So here this is separated because that is common part in both. And of course, this can be further simplified. That is 8 8s are 64. So density of a CCP unit cell is in the order of root 2 by 8 into some value. Root 2 by 8 into some value, right? Now let us find HCP. HCP, what is Z effective? 6. Molar mass m, Avogadro number. What is the volume? 24r cube by 24r cube into root 2. And now again you separate molar mass, Avogadro number, and r cube, because you can see now this part is the same. And here this is 6 1s and 6 4s. So both are same actually. Root 2 by 8. And this is also root 2 by 8. So density of CCP and density of HCP are same if the radius is same. If the radius is different, definitely the values will be different, because R plays role here, and definitely the radius is same, so density is same. So first option is correct. It can be multi. So coordination number, of course, 12 and 12. Coordination number 12 and 12 same. Fraction unoccupied, packing fraction is 0.74. 1 minus 0.74, 0.26. Of course, this is also correct. But distance between two consecutive layers, let us check. Distance between two consecutive layers. So first let us take CCP. But again here, if you want, you can watch that video. Layer view clearly I explained. And the CCP is standing on its body diagonal. Vertical height I'm taking. So this is body diagonal. This is particle of first layer, second layer, third layer, fourth layer. Now this distance is root 3a. This distance is root 3a. Understand it in a proper way, root 3a. Now he's asking this distance, vertical distance. This distance he's asking. So divide that into 3 parts. So part 1 between first layer and second layer, part 2 second layer and third layer, part 3 third layer and fourth layer. So this is here the body diagonal is, unit cell is standing on body diagonal. And the distance between two consecutive layers, if you take 1/3 of body diagonal, 1/3 of body diagonal means root 3a by 3, that is a by root 3. But which unit cell it is? CCP. In case of CCP, root 2a is equal to 4r. And I'm writing the distance between two layers in terms of radius so that we can compare. Because according to the question, he's saying radius of atom is the same. So root 2a is equal to 4r and a is equal to 4r by root 2, and substitute this a here. If you substitute this a here, a by root 3. So a is 4r by root 2, so root 3. So this will be 2r into root 2 by root 3. What is this? Distance between two consecutive layers of CCP. You have to recollect, when CCP unit cell is standing on its face, the layers are diagonal. but we need to take vertical height, distance between consecutive layers. So now the unit cell is standing on its body diagonal, and from this point to this point root 3a. From between these two, that is 1/3 of root 3a. I expressed in terms of radius because according to the question, radius is same. And in case of HCP, distance between two consecutive layers means half the height. First layer, second layer, third layer. This is height of the hexagon and half of that. So this is height of the hexagon, half of that. What is the value? 2r root 2 by root 3. Here, 2r root 2 by root 3. So they are same. So coordination number is same, density is same, distance between two consecutive layers is same, and packing fraction of unoccupied space is also same. But very clear, radius he mentioned same. Because of that reason, so the answer A, B, C, D, all the 4 options are correct. So this discussion will be helpful only if you are conceptually strong. 100% I'm telling you. So if you are conceptually strong, then you watch these videos. Otherwise, not necessary. Waste of time. Definitely, I can say that is waste of time. And the next one, which of the following is correct? Which of the following is correct about a solid element which has ABC type of packing? A is edge length of the unit cell and R is radius. He has given some options and he's saying which option is correct. Distance between the nearest octahedral and tetrahedral void is root 3a by 4. We'll calculate it. We have to check. First, okay, let us check option A. And very clear, he's talking about a CCP unit cell, ABC. Distance between nearest octahedral and tetrahedral void. See, octahedral void is body center. Tetrahedral void here, body diagonal. So 1/4 of body diagonal. This distance in the previous video, already we solved this question. So this is root 3a by 4. And this distance is root 3a by 2. And the distance between these two particles is asking. So that is root 3a by 2 minus root 3a by 4. Root 3a by 2 minus root 3a by 4. And the answer is root 3a by 4. So the first option is correct. Distance between two nearest octahedral voids is a by root 2. Distance between two nearest octahedral voids. See, for example, here, for example, I'm taking one face, edge center, edge center, edge center, edge center. And edges, sir, why are you taking edge center? Because edge center is octahedral void. And if you take these two octahedral voids, they are separated by what distance A? But what is he saying? According to the distance between the nearest octahedral voids, nearest. But if you take this one, if you take this one, so this is edge center, this is corner, and this distance is a by 2. This distance is a by 2. In that situation, this distance will be a by root 2. So this is a triangle, and you can apply that Pythagoras theorem, and you can say this is a by root 2. So body center and edge center, if you take, that is A. Between these two edge centers, if you take A, but if you take adjacent, this is one edge, this is one edge, adjacent edge centers, if you take, we'll be getting A by root 2. And we are actually getting A by root 2. But what did he give? A by root 2. Correct. Option B is correct. Distance between two nearest tetrahedral voids. Distance between two nearest tetrahedral voids. If you can recollect, I'll explain this again. See, for example, this green one, if you take, that is CCP, 1 cubic unit cell. Now you are dividing that unit cell into 8 parts. This is a bigger unit cell that is divided into 8 smaller unit cells. You can see 1, 2, 3, 4, bottom also 4. Now you please look at only smaller unit cell. Now Every body center of smaller unit cell has one particle. Every body center of smaller unit cell has one particle. In fact, that is tetrahedral void of the bigger unit cell. I have taken a cubic unit cell, divided into 8 parts. Now in the smaller unit cell, at a body center, I kept one particle. Now that body center of a smaller unit cell is tetrahedral void of bigger unit cell. In fact, that is called body diagonal. If you can recollect, yeah, this is body diagonal, right? And here, according to the question, the distance between two nearest tetrahedral voids. So you can check these two. These two are the nearest, definitely. All combinations you take. So this one you check. That is also nearest, definitely. But these two are not nearest. But here, these are nearest. See, if you carefully observe, we are talking about this unit cell. And this is A. This is A. Now, and obviously this distance will be A by 2. This distance will be A by 2. This distance also A by 2. Now, in this unit cell, this is at body center. In this unit cell, it is at body center. And from this body center to this body center, distance is asking. That means, for example, if you take this distance is A by 2, right? And here this is body center of this. This distance is A by 2. Sorry, in this half, A by 2 half, that is A by 4. Sorry, this is A by 2. Sorry, this is A by 2. This is A by 2. From body center to this, it will be A by 4. And this is also A by 4. Now, this distance is asking A by 4 plus A by 4, that is A by 2. It's a very simple question, actually. Easily you can understand. It's not a big deal. You can see here again, if you want. Here, this total distance is edge length A. Now, this is the smaller unit cell. You can see this is the smaller unit cell. So what is the edge length now of smaller unit cell? A by 2. What is this distance? A by 2. Now I am taking body center, means somehow here parallel to this. And this distance will be half of A by 2. So that is A by 4. And here also this is A by 4. A by 4 plus A by 4, that is A by 2. So the distance between two nearest tetrahedral voids in CCP unit cell is A by 2. But what did he give? In the options, he gave root 3A by 2. That is wrong. And the distance between successive A and B layers. Actually, in the previous question already we solved the distance between two consecutive layers. The distance between two consecutive layers. The unit cell is standing on its body diagonal, and this vertical height, this distance already in the previous question we solved, 2r times of root 2 by root 3. The same thing is given. So the answer is ACD. Answer is ACD. So if you do not understand, watch it again. 100% you will get the clarity. Take the help of the pictures. Take the help of the pictures, right? And the crystalline structure of magnesium is HCP. And the density of magnesium, of course, it's not a new model, because he gave Avogadro number, atomic mass values he gave, and crystalline structure of magnesium is HCP. Find the volume of the unit cell. Density is given, volume he is asking. Direct formula substitution. Atomic radius. If you know the volume, from that atomic radius you can find. Height of the hexagon. If you know the volume, you can find the height also. How many nearest neighbors does each atom have? Coordination number he's saying. Coordination number is 12. So need not to discuss this question, because it is a repeated model, and everything related to density. And of course, this is also repeated model, because the dimensions are different. And he at that question, in the previously Z effective he asked, but here it is density, but the procedure is same. Base area into height, you'll be getting volume. A and B values are given, volume of unit cell. From that Z effective I have calculated 4. Z effective I have calculated 4. The model is same. The model is same. And the next one, atoms of element B form HCP and those of element A occupy 2/3 of tetrahedral voids. Find the formula of the compound. Very simple question. Very simple actually. B is forming HCP, so Z effective is 6. A occupied 2/3 of tetrahedral void. 2/3 of tetrahedral void. Tetrahedral voids are how many? 12. 2/3 of tetrahedral void. So 8. So that is A4B3. And which of the following is correct about 3D? So that is also facts. These are all facts. And yes, these are the important models I felt in HCP. And in the next video, we'll be talking about some model questions on ionic solids and defects. This is the end of this video. Thank you. Thank you very much.